Hi, darlings. Today we've got a long list of derivatives for me to list out for you and you to put in your memories. There's going to be 7 today, and I know that sounds like a lot, but I've got all 6 trig inverses to do and then a generic inverse to do. So we're going to start with the generic inverse. So what we're doing is we're taking the derivative of f inverse of x. And I'm going to prove this one to you, and then probably none of the trigs unless I change my mind. The proofs for all 7 of these are identical. It's just the function changes depending on, which of the trig you're doing. So here's how you take derivative, or here's how you prove derivative of any inverse. You start it with that fact. So remember that an inverse switches your inputs and outputs. An inverse undoes a function. So a function and its inverse undo each other, and you're just left with the input alone. So f of f inverse is just x, because they undid each other. And then what we're going to do is we're going to do some implicit differentiation from your last video, where we're going to go and take the derivative of both sides. So don't you worry, I got the right-hand side. That's 1. On the left is a bit of a mess. So it starts with a composite function. You have f of f inverse, and that's going to take a chain rule. So you take the derivative of your outside function, f prime of f inverse, times the derivative of what's inside. Derivative of the outside at the inside times the derivative of what's inside. Well, here's what's inside. And if I could take the derivative of f inverse, I would not be in the middle of a proof for the derivative of f inverse. So we're just going to write the derivative of f inverse and leave it like that for now, forever, because we're done. Like, remember, this is what we're trying to go find. This is what we're trying to prove. And I have an equation, and I took algebra once, so we can manipulate this equation and solve for the thing we're looking for. So here it is, the derivative of f inverse of x equals 1 over f prime of f inverse. I just got that. I just divided this over to the other side, and the end. That's what you're doing. So I'm going to write that up here as the first of 7 rules that you're going to get today to memorize. This one is probably one of the most forgotten, but it's pretty simple. You just have to, if you don't have it memorized, there's nothing you can do. I mean, I guess you could go back and prove it every time you needed it, because it's a pretty quick proof, but I don't know. All right, let's get into trig. The derivative of sine inverse is 1 over root 1 minus x squared. The derivative of cosine inverse, I'm going to write arc cosine just so you remember that that's a thing, is the same thing but negative. Isn't that convenient? And then we'll do, I like tangent. So I know I'm not proving any of these, and it hurts my heart just to write them down and say go and memorize them. But it is what it is. Cotangent inverse is the same but negative. Trying to get them all on one screen so that I can get them all down. You can pause and jot them into your own notes wherever you're keeping them. This one's fun. This is x root x squared minus 1. And cosecant. Same thing but negative. So that's the good and the bad, where they're all kind of similar, but not similar enough. And then you're going to forget which one's negative. And then these two really get students. Like, is it 1 minus x squared or x squared minus 1? Usually kids don't have trouble with tangent and cotangent. That one works out pretty well. All right, let me show you how these are used then. All right, so there, pause, write them down. 5, 4, 3, 2, 1. And here's some examples. Because nobody's ever just going to ask you to take the derivative of an inverse tangent. It's always going to be mixed up with something else. So let's go and write a couple really fun functions, like e to the x times inverse cosine. So Your brains are starting to get pretty full of derivatives, but you always have to back out of it and focus on your function. This function is a product. You have two things being multiplied. One of those two things is an inverse derivative. I agree. But that doesn't matter to start. To start, we're going to start with a product rule. Product rule says first, you write it, derivative of the second. All right, I'm just going to smush it up over here. Times, it's not minus, it's times. And then root 1 minus x squared. First derivative of the second plus second, you just write it. Derivative of the first is another e to the x. The end? Sure. I don't anticipate making you clean these up very much. I mean, I kind of hate this thing that's happening here. I would rather you just do this, because I don't want you to think that it's subtraction. There you go. One more. What about if I give you, let's do secant, because that one's fun. Inverse secant of something. How about like 3x squared minus 4x? This one's going to be a doozy. This is a chain rule, because you have a function, this, that's inside of another function. So we have to do a chain rule on this. Chain rule starts with the derivative of your outside function. Secant squared is the outside function. That's the last thing that you would do. So the derivative for secant squared is 1 over, let me scroll. It's 1 over x and then x squared minus 1. But these x's are not normal plain x's. They're your input. Whatever your input to sine was, or I'm sorry, to secant was, is what has to go there. So this is going to look really strange, but it's not x, it's 3x squared minus 4x. Square root of, not x squared, but 3x squared minus 4x squared minus 1. And I have to extend this way over. That's your derivative of inverse secant at 3x squared minus 4x. Then you go and take the derivative of the inside. Well, here's your inside. Those are just really pretty power rules. And what I'm going to do is erase this and just throw it on top, because it would be out here to the side, but I think it looks prettier when it's all smushed up together. So I pull a power, subtract 1, pull a power, subtract 1. And that is that derivative. So these can start to look really strange because your input is not always just an x. Here it was. Here it was just an x, so it's just an x that's getting squared down there in your derivative. You just have to pay attention. All right. Because my heart hurts so much that I didn't prove any of these, I'm now going to prove one. So if you're good, you got it. There's your rules to go memorize. Go fly away, my birdies, and go practice. If you want to see a proof, I'm only going to do one. I'll do inverse sine just because it's the first one. I'm going to prove it the same way that we proved your f of f inverse. So I'm going to do sine of sine inverse equals x. That's a true statement. So I'm starting my proof with a true statement. And then I'm going to differentiate both sides with respect to x. All right, this is still 1. This is a chain rule. Well, the derivative of sine is cosine. So it's cosine of inverse sine times the derivative of inverse sine that we're pretending like we didn't already write down so that we can do a proof. And then just like in that f of f inverse, we're going to divide to the other side to get this piece alone. So the derivative of inverse sine is 1 over the cosine of the inverse sine of x. And now you're wondering maybe where I got all of those roots and all of those 1 minuses. This, let's talk about the inverse sine of x. So if you remember, inverses switch your inputs and your outputs. So normally we'd have sine of an angle equals a ratio. So this is the inverse sine of a ratio equals an angle. I'm going to use theta as my angle. So what this is saying is that the sine of my angle equals x. These are These are congruent statements. They say the same thing, just backwards and forwards. So I can draw this triangle. I took trig once too. It was my favorite. Was trig your favorite? It was my absolute favorite. Calculus wasn't my favorite until after I was out of calculus and I realized that it was fun. All right, sine is opposite over hypotenuse. So it's an x over 1. Opposite's x, hypotenuse is 1. And then I can find the missing side because Pythagorean theorem. So a squared plus b squared equals c squared gives this. All right, there's the triangle that we're working with. Let me come up here and rewrite this a little bit because now I'm going to think of it as 1 over the cosine of theta because inverse sine of x is just an angle, theta. Well, here's theta. Cosine is adjacent over hypotenuse. So this is 1 over root 1 minus x squared. Just like I told you, if you thought I was lying, now I've proven myself to you. So there they are. The same thing happens. Like it's the exact same proof for every single one of these. It just depends on, like this guy, we were given sine, and so we had this side length to go solve for. With the tangents, you end up finding the hypotenuse. It just depends. So you can go try some of them. You can go look them up. They exist everywhere. And I think there's other variations of it too, but this one's my favorite because I really like trig. All right, kiddos, let me know if you need anything.